she received her PhD in physics from Princeton University in 2008, under the supervision of Scott Tremaine, who's no stranger to this crowd. She was a more postdoctoral fellow at Caltech, followed by another postdoctoral position at McGill postdoctoral position at UC Irvine. Since 2013, she has been a faculty in the Physics and Astronomy Department at Ohio State University and a member of CCAPP Science Board. She was tenured in 2019. Her work is an interface of physics and astronomy, an interesting interface where she uses tools from astronomy and astrophysics to reveal the fundamental physics of dark matter. She will let us know more, I guess. And she told me that she's happy if you like to ask questions during the talk. Just raise your electronic hands on the participant side and I will let her know so I can interrupt her. And with no further interruption, I leave it to her. Please.
Okay, thank you. All right, so I'm happy to be able to give this virtual seminar today. So the subject of this talk is testing dark matter physics with galaxies. I'm going to go back and forth and talk a little bit about sort of particle properties of dark matter and dark matter's macrophysical structure in the universe and the connection between the two. But the thing that brings everything together actually is galaxies. So we're also going to talk a lot about galaxies. And this is an astronomy and astrophysics group, right? So hopefully the galaxy part at least will be exciting and familiar. So my group does some social media. We're at How We Science on Twitter and Instagram. My group is pretty diverse, and so we like to show people just how we do science and that you don't need to look like Albert Einstein to be a physicist. So if you're interested in seeing some of our shenanigans, you can follow us on Twitter and Instagram at How We Science. Okay. Sorry, got to figure out how to, there we go. So I'm going to talk about the ingredient list for the universe. So I may say something that is sacrilegious to some, but I am not a big fan of pie or pie charts. And so I prefer to illustrate the contents of the universe with my favorite dessert, which is a nice chunk of chocolate cake with some chocolate frosting on it. So this is a representation of our universe. The normal matter or familiar matter, basically everything in the standard model that isn't a photon or a neutrino, we call a baryon. And baryons make up only 4% of the energy budget of the universe. So they're like the sprinkles of the cupcake. So brightly colored, but really a very subdominant part of our universe. The cake part of this cupcake is like dark energy. So dark energy is responsible for pushing galaxies in the universe apart. And we really don't know what it is. In fact, we don't know which side of the Einstein equation it goes on. So it could either be a modification to general relativity or a new field in the universe. Okay, but the subject of this talk is the frosting, which is my favorite part of any nice piece of cake. And so the frosting in this case represents dark matter, and its proportion to the cake part of the cupcake is about right. So at least when I'm baking, so that there's about 1 part dark matter or frosting for every 2 parts dark energy or cake, or 3 parts, part and 3, something like that. And what we're going to talk about throughout this talk is really how frosting, the relationship between the frosting and sprinkles, or dark matter and baryons, is very similar. So the frosting is what holds these sprinkles onto the cake. Likewise, in our universe, the dark matter is really what holds galaxies together. So dark matter, as we're going to find out, is sort of the birthplace of galaxies. So without dark matter, without clumps of dark matter that we call halos, it's very difficult for the baryons to collect and cool and form galaxies, stars, and even us. So just as the frosting is holding the sprinkles onto the cupcake, dark matter holds the baryons together to form galaxies and everything that's on smaller scales than that. Okay, so why does dark matter matter? So I gave one example about the, dark matter being the birthplace of galaxies, but there are actually two other big reasons why dark matter matters, and figuring out what it is matters. So the first is that it shapes the growth and structure and evolution of the universe. So this is one of these beautiful images from NASA that I like to show, which shows the history of the universe from the very beginning. Can you see my cursor here? The little arrow? Okay, good.
Yes.
From the beginning, the universe rapidly expands, which is represented by this, the steep curve right here, to the era of the cosmic microwave background. And then the universe expands slowly. We see our first stars and our first galaxies. And now the expansion of the universe is accelerating in this dark energy dominated era, and we have all these beautiful galaxies that we're familiar with. But during most of this, the life of the universe, it's the dark matter that's really driving that expansion. So for most of the history of the universe, dark matter is the dominant component of the universe, and is driving not only the homogeneous expansion of the universe, but also the growth of these stars and galaxies on these small scales. So dark matter plays a key role, or for much of the history, the dominant role in the evolution of the universe and the growth of structure. But the other reason why dark matter matters is that it's a window beyond the physics of the standard model. So everything that is really familiar to us that we probe in the lab or see with our eyes is made up of standard model particles. So we got our quarks, we got our leptons, we have our mediating particles, so our gluons, photons, and W and Z bosons. And we've got our Higgs particle as well. So everything that's really familiar to us is in the standard model. But dark matter is nowhere to be found in here. So dark matter is almost certainly a new species of particle, or several new species of particle that are not described by the standard model, and that in fact are in a theory that is yet to be determined, which encompasses that dark matter and the standard model are all encompassed in the same big, as yet non-determined theory of everything. Okay, so in short, dark matter matters for the evolution of our universe, as well as for the contents of the universe. Okay, and there are many models for dark matter. So theorists are extremely creative, and there are many different beyond the standard model theories, and those theories have good dark matter candidates in them. So this is a plot that I took from a talk by Tim Tate, which I think pretty much every dark matter talk now has in it, because it's just so great. But there are many theories beyond standard model theories, which are represented by these ovals or part ovals. And then the dark matter particles in those theories are represented sort of within this red shaded region. Of particular interest is a class of dark matter particle called the weakly interacting massive particle, or WIMP, a term coined by my late colleague, Gary Steigman. And that's sort of, so many of these extensions to the standard model have a sort of WIMP-like particle. And so it's sort of one of these like natural type particle models that a lot of people have invested tremendous energy to investigate. So in particular in Canada at Snow Lab, there are a number of experiments located or that will be located to probe WIMP-like dark matter. Okay, so there are many models for dark matter. So how do we figure out which, if any of these, is the right description of dark matter? So there are the traditional laboratory searches, which I'll describe in brief. So perhaps the most spectacular is what happens at colliders like the Large Hadron Collider in Switzerland and France, or there are also other experiments for other types of dark matter that people are searching for, where you try to create dark matter in the lab. So in the case of a WIMP-like dark matter particle at a collider like the Large Hadron Collider, what you do is you accelerate standard model particles. In the case of the LHC right now, it's protons, and you smash them, and then out comes a bunch of stuff that you can see and detect and characterize. And then the key signature of dark matter is that you have some missing energy. So you can figure out what the center of mass energy is before collision, and you know what the total momentum is, center of mass momentum. And then you look for a missing piece when you're summing up the energy and momenta of the components after the collision. In practice, it's much more complicated than that, but that's sort of the basic idea of how you make and then know that you've made dark matter in the lab. Okay, so you can also destroy dark matter. So this happens actually naturally in the universe, which is that wherever you have an dark matter, if dark matter is its own antiparticle, which for the WIMP type paradigm we think is likely, then when the dark matter particles encounter each other, they can annihilate and produce a bunch of particles which either directly are standard model particles, or maybe you have other hidden sector particles that then can decay into standard model particles. But in any case, you try to detect the leftovers, the detritus from this annihilation event using a space telescope or a ground-based air shower array. And in this case, I'm showing a picture of the Fermi Gamma Ray Space Telescope, which to date has set some of the strongest constraints on WIMP-like dark matter based on annihilation of dark matter in cosmic structures, including dark matter halos. Okay, and the search for dark matter is a major goal for basically every cosmic ray, gamma ray, neutrino experiment. Okay, the final lab-based approach, and this is one where again Snow Lab is playing a major role, hosting many different variants of these experiments, is direct detection. So in this case, we take the fact that our Milky Way is embedded in a big cloud of dark matter that we call a halo, and we look for interactions of the dark matter in our Milky Way's halo with nuclei, or in some cases electrons, in our instrumented volumes underground. So in this case, you have a dark matter particle coming in, bumping into a nucleus, and then that nucleus goes recoiling. And it's that recoil that these experiments, these direct detection experiments, are trying to measure. So just to give you some perspective, the typical kinetic energy of a nucleus coming from one of these recoils is about the same as the kinetic energy of a red blood cell in one of your capillaries. Okay, and so we're looking for one of those events per ton of material per year, and be confident that that's not any one of any other backgrounds that might be going on in your experiment. Okay, so those are the three pillars of sort of experimental searches for dark matter and probes. So we've got creation in the lab, we've got destruction throughout the cosmos that we try to measure with cosmic ray telescopes, and direct detection, so looking for typically elastic interactions in the laboratory. Let me stop here and ask for questions before I go on to the more astrophysics part. Do we have any questions so far?
Yeah, I don't see any raised hands. Welcome to unmute yourself if anyone has a question. Okay, I guess you can continue.
Okay, great. Okay. All right. So what I want to do, and what I'm going to focus on for the rest of the talk, is using the cosmos, which as I'll tell you in a second, is the original laboratory for dark matter physics, and see how we can use the cosmos to further sharpen our knowledge of dark matter microphysics. So basically, what is being able to reveal the fundamental particle physics of properties of dark matter by using the tools of astronomy. Okay, so the theme for this talk, I realize that this image sort of age dates me and location dates my childhood, but there we go. So the goal of this talk is, or the message is, by measuring where dark matter is, we can find out what dark matter is, and we're going to use galaxies to do it. Okay, so to sort of set up this notion, I'm going to ask, how do we see the invisible? So the analogy I like to give for dark matter is air. Usually if we were all together in a lecture hall, I would be able to make a more specific analogy, which is that the fact that I can see people in a lecture hall, even if they're far away, the fact that I can see them at all tells me that air has very little interaction probability with light. Okay, so how would I know that the air is there if I can't see it? And again, part of what tells me that I can't see it is because I could see you through this large column of air. How could I tell it's there? Well, I could tell that air is there, you know, even if I didn't know anything about its necessity for human function. But I could tell it's there because of how air acts on things that I can see. So an example is this windmill farm in Southern California. In this case, I know that the air is there because there's a wind that's pushing these blades of these fans. So I can tell that the air is there because of its effect on these things that I can see. The same thing is true with dark matter and galaxies. So let's consider the motion in galaxies. So this is sort of a artist's conception of a galaxy. So my usual question that I ask basically every audience is, what's wrong with this galaxy? How do we know this is not a real galaxy other than the fact that it's clearly a GIF? I know we have some dynamicists in the audience, so what's the giveaway?
Rotation.
Rotate like solid bodies.
Yeah, so this is a solid body rotator. So like if you're spinning a can of soup and just looking at the top of the lid of the can, it's a solid body rotator. Galaxies are not, as you know, solid body rotators. You have differential rotation. So the inner parts spin, have a larger angular speed than the outer parts. It's good. So let's see what we can learn about the contents of this galaxy just based on how it's rotating. So what we know is, if we imagine that this were spherically symmetric, which clearly it's not, but you know, for physicists, we're going to do the spherical cow approach, or in this case, spherical galaxy. In this case, there's a close and well-established relationship between the speed at which particles on circular orbits go and the enclosed mass within that orbit. So if we find that stars or gas clouds in a spiral galaxy like this, where really the gas clouds and stars are in nearly circular orbits, if we find that those particles or clouds are moving slowly, that tells us that there's not that much mass enclosed. So then what happens if the galaxy is faster? What is that telling us? It's telling us that there is more mass enclosed. And so this has historically been the sort of first way that we realized that something like dark matter had to exist, is that we noticed that the internal motions of galaxies, as well as the motions of galaxies within larger systems called clusters. So you have an ensemble of galaxies, gravitationally bound. You can measure the mass of that system by looking at the motions of individual galaxies. That method was first explored by Fritz Zwicky in like the 1930s. But sorry, my kid is, I think, trying to play hide and seek with his dad right now. Okay, so we can use the motions, both the internal motions within galaxies, as well as the motions of the galaxies themselves, to measure mass on a variety of scales. And what we find is things moving faster than we expect based on the baryons alone. So in the context of motions within galaxies, we owe a debt to Vera Rubin and her collaborators, who starting in the 1960s on, carefully characterized the motions of stars and gas clouds within galaxies, to find that basically the velocities of the components of galaxies are almost constant as a function of distance. One of the beautiful plots from one of her early papers is this rotation curve of the Andromeda galaxy. So she took spectra of these H2 regions in the Andromeda galaxy, and from those data was able to reconstruct this rotation curve of Andromeda out to sort of past 20 kiloparsecs, which is quite far. So that's well outside the optical radius of the galaxy. And she found that this rotation curve was completely flat. Now, if all that was within the Andromeda were the optical producing things in here, then you would expect that outside the optical radius that the rotation curve would go down, right? Because you're getting farther away from your gravitating mass. But instead, she found this fairly flat rotation curve. Okay, and that was the first strong evidence that galaxies live within these self-gravitating, massive, puffy, dark matter structures called halos. Now, this image is not even to scale. I mean, the only reason I've blown up this galaxy this much is so that you can see it on here. But typically the linear size of the dark matter halo is a factor of almost 100 larger than the optical radius. So imagine a little teeny galaxy and a giant fluffy halo. And so the galaxy really sort of signposts the fact that you've got this large dark matter structure in space. Okay, and one of the great things then is that we can use the fact that every galaxy is signposting a dark matter halo to basically use galaxies as our way of locating dark matter and mapping out the number and structure of these dark matter halos. So here I've taken a couple of galaxies that I'm going to refer back to again later. So I've got two companions of the Milky Way. I've got the Fornax dwarf galaxy. This is an image I made using data from the Assassin survey, which is a transient survey at Ohio State.
The screen is black. Is that supposed to be?
He's frozen.
I think we might have lost Annika.
No, maybe give it a minute or so.
Yeah, Michael says it's dark matter, so. It's like, I guess we should wait to detect dark matter.
I see her on chat. Let me see if she can read her messages. Oh, no, we lost her. How about we wait a few minutes? Her computer just rebooted. She'll be back soon. Okay.
Hi, sorry about my computer suddenly rebooted itself.
That's okay.
I apologize, you might hear the fan going a little bit. I don't know what's going on. All right, should I just resume?
Sure, yeah, please go ahead.
Okay, and what was the last thing that you heard me say?
So you moved on to a couple of galaxies, yes, but
Okay.
Oh yeah, I guess we got it now. Yeah.
Okay, good. All right, so we're going to use galaxies to find where dark matter halos are. So we're going to count them. And we also need to know what the mass of these halos are, which I'm going to talk about in a second. But we're going to use galaxies of different sizes to find where the dark matter halos are. Why is that important? It's because different theories of dark matter make different predictions for how many dark matter halos there are as a function of mass. And they also, different theories of dark matter also predict different internal structures for the dark matter halos. So for the rest of this talk, I'm going to focus on the number of dark matter halos as a function of mass. I will not focus on the internal structure of these dark matter halos, but that is also very important. Okay, but these are different pictures that I have taken from the literature of different dark matter models. So this cold matter model is sort of like a WIMP-like dark matter model. So we see structures that look like this, where we have a big dark matter halo, and then it has many, many smaller dark matter halos in it that we call subhalos. You'll see that for this warm dark matter model, where dark matter is semi-relativistic at its birth epoch, there are far fewer small dark matter halos. That's true too. This is a plot taken from one of my papers with Mei Wang, who's currently a McWilliams Fellow at Carnegie Mellon. This is a late decaying dark matter model. And then perhaps one of the most amazing dark matter models in terms of sheer beauty and interestingness of structure of both the theory as well as the cosmic structure predictions are these fuzzy dark matter or axion-like particle models, where here the de Broglie wavelength is so large that what we're seeing is interference patterns for this fuzzy dark matter case. Okay, and so the idea, so we're going to focus for this talk on predictions of this cold dark matter or WIMP-like dark matter model, just because it is the dominant paradigm for what dark matter is. So dark matter may not be cold dark matter. It may not be WIMPs at all. It may be something totally different, but this is sort of the simplest model that works reasonably well on at least large scales. So it is sort of the thing that we're always responding to when we're looking at new dark matter candidates or making new large scale structure predictions, is that they're always sort of in response to the simple cold dark matter model. So cold dark matter is dark matter that's basically non-relativistic when it's born in the early universe. That's how we get the name cold. So cold, like non-relativistic, as opposed to hot or relativistic. So it's non-relativistic at its birth epoch. It's stable on long time scales, and it hardly interacts with us beyond gravity. Those are the sort of physical building blocks of this cold dark matter paradigm. Now, this is nearly synonymous with WIMP, or this weakly interacting massive particle. So the WIMP is not the only cold dark matter candidate. So QCD axions are also cold dark matter candidates. But for many people, I think WIMP and cold dark matter, or CDM, are almost synonymous. They're not exactly the same thing. The WIMP is but one example of a cold dark matter candidate, but it's sort of the thing that a lot of people, including me, just sort of always have at the back of our head, because it's sort of like the best motivated dark matter candidate. Okay, so this is the thing that we're going to test. Okay, and probably the most striking prediction of this paradigm on macroscopic scales. So all of these things that I described before, these are really properties of the particle physics of the cold dark matter model. So the fact that something is stable in long times, that it's not relativistic when it's born, all of these things come from the interaction, the couplings among particles in the early universe, and maybe about the symmetries. So all of these statements that I made that are sort of qualitative, they come out of really, specific theoretical models. But it has implications for the macrophysical structure in the universe. So the most important prediction of the cold dark matter paradigm is that we have dark matter halos on all scales, from like galaxy cluster scales, so 10 to the 15 solar masses, down to sort of Earth mass scales. And the cold dark matter paradigm also makes a prediction of the structure of that hierarchy. Okay, so how many more Earth mass halos there are versus like Milky Way mass dark matter halos. And so that is the strongest prediction of this paradigm. Every other dark matter model will make a different prediction on especially the smallest of those scales. There have been a number of papers. Actually, there was a brief flurry in the mid-2000s and another brief flurry just in the past year or two of simulations of the smallest dark matter halos that form in these cold dark matter paradigms. And so here we have this redshift slice where you see teeny tiny Earth mass halos. And then this is a slice from the Aquarius simulations by Volker Springer, where you see like a Milky Way mass dark matter halo. Okay. So what we really want to do is we want to find and count these little matter halos, because that's going to tell us if this cold dark matter or CDM paradigm is getting things right or if it's not. Because again, many of these theories that are not cold dark matter theories basically don't have any dark matter halos below some specific scale. Okay, so the key now is that we're going to try to count these halos with galaxies. As I'm going to discuss a little bit, that there's some complications with that, but since we know that every galaxy must be in a halo, we can use the presence of galaxies to signpost these halos. And the smaller the galaxy, the better, because we think they're just like there's a hierarchy of dark matter halos, that hierarchy is mimicked in the galaxy world. So that basically your big galaxies are going to be living in the big halos and the little galaxies in the little halos. Okay, and importantly, if there's no halo, there won't be a galaxy. So if you count a bunch of galaxies and you don't find as many as you would expect for cold dark matter theories for a specific scale, that tells you that perhaps you're missing a bunch of dark matter halos relative to cold dark matter predictions. Okay, so I realized I went through that a little fast. Are there questions about these different models and the galaxy halo connection, which I'm going to get a little deeper into in the next few slides?
I have a question.
Sure.
Go ahead.
Yeah, there's this other proposal called the FIMP mechanism where the dark matter freezes in out of equilibrium. Do you consider that cold or not cold or warm?
Oh, so that is a good question. I have not done a deep dive on FIMPs recently, but what I would say is cold versus not cold, I would characterize based on the momentum distribution of the particles when they freeze in. So if they're not very relativistic, I would consider that a cold dark matter candidate. If the momentum distribution is skewed toward the relativistic end, then I would consider that to be not cold dark matter. But it's really about the momentum distribution at the birth epoch.
Okay, because there seem to be both kinds. I've seen non-relativistic FIMP and I've seen relativistic FIMP. So I guess it spreads across. Okay.
Yeah, and that's actually fairly common for dark matter models, that they, for a particular particle model, depending on which parameters you have in that model, they get classified in terms of their effective cosmic structure, depending on whether really it's about this momentum distribution. So, you know, for example, sterile neutrinos are a candidate where you can have either a hot, warm, or cold sterile neutrino, depending on exactly like the mixing angle and so forth in the early universe. Good. Okay. So what I'm going to say up front, and these are the things that we're going to consider for the rest of this talk, is that there's so far two issues when you're trying to count halos by counting galaxies. And these are the things that my group is really trying to address through a variety of projects right now. So one question is, have we properly counted galaxies, especially the little ones? I'm going to argue the answer so far is no, but we're working on it. And the other big sticky point is, how do galaxies inhabit halos, especially on these very small scales? And I would say that's still something that we're working on as well, which we'll see throughout this relation. So fundamentally, so I'm going to come back to galaxy searches in a bit. The first thing that I want to talk about is that second question that I asked about how galaxies inhabit halos. So this is basically the question of, if you have a galaxy of a certain stellar mass, does it live in a small dark matter halo or a big dark matter halo, where we're going to quantify small and big more throughout the talk. And so we call this the stellar mass halo mass relation, or I'm just going to call it M star M halo sometimes. But this is sort of like the underlying question of how do you put a galaxy that looks like this into a halo? Okay, and so I'm going to focus on this point a little bit first because we're going to see that the uncertainties there have some consequences later. So what I'm showing here is a sort of a galaxy baryon mass function. So this is basically the number density of halos in the universe as a function, or the number density of galaxies as a function of the total mass of like stars and cold gas. And it's compared against a cold dark matter halo mass function. Okay, so this is the number density of halos per unit for each as a function of halo mass. So in this case, this is an older baryon mass function by Baldry et al. From the Sloan survey. There have been some more recent works, for example, coming out of the Gamma survey. And one way that people try to assign galaxies to halos is they take this notion that there's this hierarchy in both galaxies and halos, and say basically big galaxies live in big halos, little galaxies live in little halos, and let's populate the galaxies hierarchically. Let's see where the number densities of galaxies above some baryon mass matches the number of dark matter halos above some halo mass. And that correspondence is shown here in purple. So at constant number density, what is the galaxy mass that corresponds to this halo mass of fixed number density? We call this method of shoving a galaxy into a halo abundance matching, because we're really assigning stellar masses to halo masses by just looking at their abundances and matching galaxies to halos where their abundances match. And so this is, so starting around 2004 or so and forward, especially through the work of Iro Tazitsiomi, who was a postdoc at Princeton when I was a grad student there, and Charlie Conroy, Risa Wexler, and others, they sort of, and Andre Kravtsov, they sort of got this type of matching rolling. And what we find is that when you do this abundance matching, so this is a plot I pulled from the review paper by Risa Wexler and Jeremy Tinker, is that for these massive scales where you've got big, beautiful Hubble sequence galaxies, these abundance matching methods all give you a consistent result. And these results, this matching approach, seems to be validated by gravitational lensing. So you can also measure the halo masses of galaxies by gravitational lensing. And so far we get a consistent result that this abundance matching for putting galaxies in halos agrees well with other methods of figuring out the masses of galaxies. Now, one thing that you'll see here is all of these abundance matching method relations sort of diverge at small halo mass. Here, small is, what I mean by small is less than 10 to the 11 solar masses for the halo mass. That's about the mass of the dark matter halo of the Large Magellanic Cloud, we think. But below here is where we would especially like to use galaxies to count dark matter halos. And unfortunately, the relations are very uncertain. So this gray region up here basically shows where the data are to have done this abundance type matching. And we just don't have very complete catalogs below the scale. And so all of these lines here are really extrapolations from this most massive end. Okay, so extrapolated, measured. And unfortunately, this extrapolated region is the most interesting region. So if you look at this extrapolation further, this is a plot that I made with Greg Dooley a couple of years ago, where we just sort of extrapolated these relations. You can see, for example, for a 10 to the 5 solar mass galaxy. And I'm going to talk about this in a bit, but we think in the Milky Way, at least, we've counted all the galaxies that are this massive. We get like, you know, an order of magnitude plus difference in sort of the mass that we think that, the halo mass that we think a galaxy of this mass might live in. And so that really complicates our counting of dark matter halos with galaxies if we don't exactly understand this relationship between the galaxy and the halo it inhabits. Okay, so that's a complication that I'm going to talk about in a bit. So as I mentioned before, we have two problems. We don't really have very complete censuses of galaxies. So even if we exactly knew the relationship between the mass of the baryonic part of the galaxy and the halo, because our surveys are very incomplete, we don't then actually know how many halos there are. But then we have this additional complication that we don't exactly understand this relationship between the baryonic part of the galaxy and its dark matter halo. So I'm going to address the first problem and then talk a bit about the second, and then go back to the first problem again. So there's one part of the universe where we can get a pretty good sample of small galaxies, and that is the Milky Way's satellite galaxy system. So this is a plot I pulled from a paper by Alex Wagner, showing in red the recently discovered satellites of the Milky Way from the Dark Energy Survey, and then in these other colors marking satellites of the Milky Way that had previously been identified. Now, this plot is already out of date because a number more satellites have been found. But these galaxies, these satellites of the Milky Way span quite a range of properties. So we've got big satellites like Fornax, which is about 10 to the 7 solar masses. And then most of the satellites that have been found are very low mass. So they've got 1,000 solar masses in stars or less. In fact, I believe Dark Energy Survey identified a galaxy that only has 100 solar masses in stars, which there are any stellar physicists in the audience, you'll be laughing because it's possible to have individual stars that are as massive as some of these teeny tiny galaxies. Okay, so this is awesome. We actually can't get censuses of galaxies this tiny anywhere outside the Milky Way because there are just so few stars. So good luck looking for that needle in the haystack of the universe outside the Milky Way. And so one of the questions that my former student Stacy Kim and I set out to answer is, okay, so we see these satellites of the Milky Way. What can we expect for the full population of satellites of the Milky Way? And how does that compare with cold dark matter theory, with these various different hypotheses for how galaxies inhabit dark matter halos? Okay, so let me talk about the first question of, based on the galaxies that we do see, what can we learn about the satellite population of the Milky Way as a whole? So one question you can ask is, where can I see a galaxy as massive and as high surface brightness as Fornax? So the answer is that we can detect a Fornax-like galaxy reliably to distances well outside the Milky Way's virial radius. So a galaxy like Fornax is pretty easy to find. We think that in the Milky Way, we've identified every satellite that is as massive as Fornax. You really just cannot miss it in the sky. However, for a galaxy as teeny and as low of surface brightness as Segway 1, we can only detect it at least with the Sloan Digital Sky Survey, which is the survey that revealed the existence of this galaxy. We only were able to find it barely with that survey. So if you look at the work by Sergei Kapasov and Beth Willman, they showed that basically Segway 1 was as far away as it could be and still be detected in Sloan. So it's about 25 kiloparsecs away from us, and it was sort of at the edge of detection there. So Segway 1 could only be found sort of in this patch. Okay, so that means that for this whole Milky Way halo, for Segway 1-like galaxies, we only probe this very tiny region of space. Okay, so the question is, how representative is Segway 1 here of the whole population of Segway 1-like galaxies throughout the Milky Way? So for this, in order to say based on here, what we see here, how many Segway 1-like galaxies are around here, we have to know something about the distribution of galaxies throughout a halo of size of the Milky Way. And that's actually kind of a problem because this is quite theoretically uncertain, believe it or not, and the subject of hot debates between simulators. So there's some people like Carlos Frank who say that small galaxies are quite robust to especially tidal disruption. And so what you should expect to see is a fairly centrally concentrated distribution of satellites in a Milky Way type galaxy, so that there are relatively many Segway 1s in this patch than there are in this whole halo. Okay, so that would be one theory, that satellites are really robust to tidal disruption. And so, so there should be relatively many Segway 1s close to us. On the other hand, some would argue, well, the simulations don't really show that. So if you have simulations that only have dark matter, even without baryons, galaxies, or the subhalos that galaxies live in, look more disrupted than what Carlos might think. So Carlos and other people would argue that the simulations actually do not really capture the tidal disruption history well. I'm sure there are many of you in the audience who have opinions about this, but they say they're numerical artifacts, so you shouldn't believe this, you should believe that. And then there are people who simulate systems with baryons, and the disk of the Milky Way, they argue, destroys many, many Segway-like 1 galaxies. So they argue that compared to the satellite population as a whole, you should see very few Segway 1s in this little region. And the way I've illustrated this is with Cookie Monster. So the bigger Cookie Monster is, the better he is at chomping down on satellites and removing them from your satellite sample. Okay, so what you can do is, if you have an idea of how robust galaxies are to satellite disruption, you can take the number of galaxies that you see in your survey out to the distance at which you can see them, and you can extrapolate for the halo as a whole. And so if you do that, you find that for a Carlos Frank type model, where satellites are very robust to disruption, that you expect to see relatively few satellites in the entire halo of the Milky Way. Just because he would argue that you are capturing relatively more Segway 1 type galaxies in your survey than in the case where you believe that tidal disruption is very, very efficient and you just should not see many Segway 1s close by. Okay, so you get a very wide range of predictions of what the total satellite population of the Milky Way looks like based on the satellite galaxies that we do see, and our hypothesis for how these galaxies are distributed throughout the halo, which is really synonymous with this idea of how robust satellites are to tides. Okay, so this figure is a bit complicated, but let me show what's going on here. So in 1999, there were only 11 known satellites of the Milky Way. And so at that point, when simulators were simulating halos, they saw that there were many subhalos, and they called this the missing satellites problem, that there were very few observed satellites of the Milky Way, yet simulations had many subhalos. Since then, a couple things have changed. One is that we now know of many more satellites of the Milky Way, and we can estimate what the whole population of Milky Way satellites are based on what we see. So these models in orange, blue, and green. So this is the number of satellites we see today. these that we know exist, these orange, blue, and green regions denote, for the Carlos Frank type model, where satellites are very robust to tidal disruption, how many galaxies we expect for the whole halo of the Milky Way. This is for our medium tidal disruption model. And this is, if you believe this gray region represents the total population of Milky Way satellites, brighter than Segway 1, if you believe that satellites are very easily destroyed by the Milky Way disk. What I'm showing in this gray region are predictions for how many satellites the Milky Way should have based on a cold dark matter hypothesis layered on with these different abundance matching models. So this green dashed model by Baruzzi et al. Gives you the highest number of predicted satellites. And this model by Brook et al. Actually, they're already, even without doing this thing that we call a completeness correction, we already know of more satellites of the Milky Way than this model would predict. The truth, we think, is somewhere near this Moster et al. Line in terms of the relationship between stellar mass and halo mass. This model fits reasonably well hydro simulation predictions for the relationship between stellar mass and halo mass. And it's sort of our medium model. Okay, and so the thing that we see is that this Moster et al. Model, which is cold dark matter with the sort of median stellar mass, halo mass, or abundance matching relation, exactly goes through these most conservative estimates for the total population of Milky Way satellites based on the satellites that we see in that completeness correction, that extrapolation of how many galaxies we see in our survey to the whole volume of the Milky Way. Okay, and in fact, for these more aggressive tidal stripping models, we have what Stacy calls a too many satellites problem. And so that is thorny. Okay, so we've gone from this era where maybe there were not enough satellites of the Milky Way to maybe there actually being more than we expected. And so that is a pretty interesting flipping of the script on the status of cold dark matter on small scales. But one correspondence is that there is not that much space for new physics. So it looks like cold dark matter sort of marginally fits, but you can't really reduce the number of subhalos or satellite galaxies and still be consistent with what we observe. Okay, so so there's not much wiggle room for any dark matter model, which tries to cut down on the number of small systems. One thing I'll say briefly, I know I'm basically out of time, is that we always worry that we're over-tuning to the Milky Way. So one of the things that my group is doing is trying to take careful censuses of satellites of other systems. So I'm involved in a number of surveys. I'll just briefly say our big work right now is for the survey called LBT Song. It's part of the thesis of 3 of my graduate students. And we have our first paper where we describe 2 new satellites of the spiral galaxy NGC 628. We are validating these candidates right now with this method of surface brightness fluctuation, which I can talk about in questions. And that work is driven by Johnny Greco, who's a postdoc at OSU, and Kirsten Casey, who's one of my students. We're also working on another survey called MADCACH, where we're surveying the satellite systems of LMC analogs. My student Chris Garling is taking the lead on that. We're also doing MADCACH basically at high redshift, and my student Daniela is working on that along with JPL postdoc Anna Nierenberg. And our group is now working in the dark energy survey to look at satellite systems in postdoc Amy Sardone's Imagine H1 survey. So we're going to have more data, and that will be great. In the future, LSST and WFIRST are going to be amazing for counting galaxies. And not just counting them, but using methods like gravitational lensing to really validate the stellar mass-halo mass relation. Okay, all right, so I will end here just to say that different theories of dark matter predict different abundances of small dark matter halos. And the primary way my group has been trying to validate these theories or test them is to count galaxies. And so we're also trying to test this idea of how galaxies and halos are connected to each other to really do a robust count of dark matter halos. And I really think this is a problem that we can really solve with data, especially with the upcoming wide field surveys. Thanks, I'll stop here.
Thank you, Annika, for a very nice talk and ending right on time, despite the disruption. Okay, questions?
Well, maybe just a comment, a trivial comment at that. You mentioned abundance matching. The person who actually invented that is Mike Hudson, who's in the audience here virtually.
Oh, great. I am sorry that your key role is not always as represented in the literature or known by people like me as we should.
No worries. I did have a question actually, since I'm speaking. Segue 1 is presumably the detection of these things is limited by surface brightness, right?
Mm-hmm.
The surface brightness is to first order distance. So why does it set a distance limit on, I mean, why is there a hard distance limit on Segway 1? If you put it further away, surface brightness stays the same, it just becomes a little bit more compact, I guess.
Yeah, so in the case of Segway 1, it's really that it was found using individual stars, like looking at an overdensity of stars. And for that, that becomes really a magnitude limit for the tip of your red giant branch. And if you have enough stars, and then if you can filter them out over the background of honestly high redshift galaxies, the star galaxy separation starts to be extremely important as you push down to lower magnitude, or sorry, higher magnitudes, a heat magnitude.
I got it.
Yeah.
Okay, I see Neil has a question. Neil, go ahead.
Yeah. Hey, Annika.
Hey, Neil.
So I had two questions, I guess. So my first question was about like the scatter, I guess, between stellar mass and halo mass.
Mm-hmm.
You know, so for small halos, it seems pretty clear that the scatter can be quite large.
Yes.
So in your modeling, do you guys assume that there's no scatter? And if there is scatter, like, you know, what impact does that have?
Yeah, so in Stacy's paper, we basically didn't explicitly put in scatter, but we did basically bracket predictions by the sort of most extreme mean relations, which in some sense is like, it's a little bit like trying to capture a little bit the scattered, like the most or at all relation. Going forward, I think putting scatter in properly is important. There's this paper by Shea, Garrison, Kimmel where he played around with increasing the scatter for smaller masses. But I think that's something that could actually be pretty easily sort of be parameterized and just dumped in the models.
Mm-hmm, I see, okay. But so far you're saying people haven't really explored it like a huge amount.
Yeah, and part of that is, I think that just the data aren't there on satellite or even just field galaxy luminosity functions below about an SMC mass. I mean, the local volume is extremely incomplete below like SMC scales. So I think that's a question where we need more data before we can really address.
Okay, I see. And my second question was about, you know, the correction that you do for the possible, you know, tidal disruption of these small objects.
Mm-hmm.
So I didn't quite maybe follow exactly. So perhaps I just missed something. So for this correction, do you assume that the correction factor doesn't depend on the presence or absence of like a big galaxy or a small galaxy, you know, because that can affect, you know, the survival of some small halo, right?
Yeah. So for the radial distributions, these completeness corrections, we just used essentially the radial distribution that comes out of having a hypothesis for, you know, how important tides are or not. Now, for an individual galaxy, if you had some idea of its tidal state, you would be able to do a better job of doing this completeness correction. You could do it in more detail, but the way the tidal stripping really played in here is that it your notions of how strong it is then affect very strongly the radial distribution within the halo.
Right. I mean, like so you see some number of galaxies, you know, as a function of like brightness or stellar mass, as a function of distance, right?
Yep.
And then you're trying to apply some sort of radial and also angle dependent correction.
Yep.
But that correction, well, right, I mean, but is that correction, I guess, also dependent on like the stellar mass?
It could be. And that's something that I would like to explore and understand better. I think one of the tricky things is also in a simulation, what do you consider to be an intact galaxy versus something that's tidally stripped versus, you know, a stream? And how do you make that correspondence to observation? So I think there's a real gap in how we talk about satellites in simulation versus how we observe them to be in our universe. You know, that's not exactly the question that you were asking, but that is something that
I'm actually not even sure anymore about my question. It might not be well posed.
Yeah.
Okay, James has a question. Go ahead, please.
Yeah, hi, thanks. Great talk, Annika. I actually, my first comment was sort of like Neil's comment that you talked about a single, you know, one-to-one stellar to halo mass relation. And yeah, I mean, I thought there was a fair amount of evidence that actually there must be very large scatter at the low mass, in particular with field galaxies. So I think there was work by Sarah Miller, for instance, looking at field galaxy dynamics that showed that you have some things with very low stellar masses that look like they're residing in quite different mass halos from the galaxies we know locally. But
yeah, so my comment on that is the one thing that I did not touch on here because it would have made this talk about 3 times as long is how we actually assign galaxies to halos in non-abundance matching ways. So this kinematic way that Sarah did, you get a totally different answer than if you do an abundance matching.
Yeah, but I think this was showing that at least for some individual objects, the halo mass is probably quite different from the answer you get abundance matching. So there's probably some scatter there. So I guess what's kind of interested me is, well, if there's scatter, it must be driven by something. So what's the physical thing that drives it? And that sort of, you know, raised a second question or comment, which was, you talked a lot about, you know, missing satellites. There are too few, overabundant satellites, there are too many. I kind of feel it should be a multidimensional plot, right? Like we should be matching things up on more than one axis. And it's not just a question of raw numbers, it's a question of maybe radial dependence, maybe also, you know, densities or peak velocity, right?
Yeah, I totally agree. And actually the thing that Stacy and I are wrapping up right now is taking the kinematic part, like not the orbits, but looking at the sort of velocity dispersions of stars within the satellites to do sort of like an old school missing satellites where we use the velocities instead of luminosity. But yeah, I totally agree. It's a multi-dimensional problem. And there were simulations by Mike Boyle and Colchin's group. You know, they were only simulating like 10 to the 10 solar mass halos, and they found like a factor of 10 difference in the stellar mass by redshift 0. So yeah, there's a lot of scatter. It would be great to have to really quantify the origins of that.
Okay, let's see. I don't have any other question from audience. Maybe I ask two final questions. One is, as an outsider, how much should I put my faith in these simulations that have baryonic implementation in them? Are they still at the, I mean, or their prediction?
So I would say that they are always getting better. You know, the state of simulations now versus like when I was in grad school, it's like astounding how much better they are. But I think there's still some issues. One is that you're not ever simulating sort of like ab initio physics. You always have some sort of recipe for every baryonic process. And in fact, the different groups will have different, simulation groups have different recipes for things like supernova feedback, and they get somewhat different answers. Things are now consistently always going in the same direction, but there are still real differences in the results that, you know, occasionally Carlos Frank's group will have some inflammatory title of a paper, which is basically like, all you other people are wrong. Anyways, not to pick on him exactly, but you know, there are, you know, so that is one issue. And then I think this issue of numerical resolution, especially as you're looking for the tidal stripping history for satellites, that's a problem still even for dark matter only simulations. It's something that Frank van den Bosch and his group and others have really been worried about a lot. So, so I would say there's a ton of progress, but there's still a lot of issues. And also because the simulations are so expensive, only specific types of systems have really been simulated in detail. There are a lot of other potentially interesting systems that just haven't gotten the theory attention that they maybe should.
Okay, and then one last thing, maybe you can comment on the detection, like which avenue do you see us finally maybe getting, like, do you see promise in direct detection or?
I think, you know, the problem is, you know, unlike dark energy, you know, we know a lot about dark matter already, but we don't know enough to have a really specific concrete model. So dark energy is a case where we basically have Taylor expanded our ignorance when we're trying to make measurements. But for dark matter, we know enough to have some sense of what might be possible. We just don't know what of 1,000 possibilities is real. So I still think that the types of WIMPs that these many direct detection searches are targeting is like one of our most elegant ideas. And we absolutely have to test it because of its connection often to supersymmetric beyond standard models. But it could be that dark matter is not WIMPs at all, and these experiments may not see anything. Or, you know, the flavor of MSSM or flavor of supersymmetry that the universe has might, you know, make direct detection difficult. We just don't know. So I'm really hopeful there's a lot of parameter space these direct detection experiments can still cover. But if they still don't find anything, you know, that just is what it is. So I'm kind of agnostic on that, but I really hope they find something soon. I wrote a lot of theory papers that will never be useful unless they detect something soon.
Okay, thank you. That was a very nice talk.
I just have a comment that if you really hope that they find something soon, that means you're not agnostic.
Yeah, true. But if they don't, I'm not going to be like bummed. Only a little bit. Yeah, but I take your point.
You have tenure already.
Yeah.
Even people who have tenure can be bummed.
Okay, thank you again for accepting our invitation. Hopefully we see you in person at some point next time.
Yeah. Thank you so much for the invitation. It's nice to see so many familiar faces.
Take care, everybody, and stay safe. Bye.
Thanks a lot. Bye-bye.
Thanks, Annika.